Hello, everyone. So the first part of this course is going to look at several techniques for integrating different types of functions. And the first one that we're going to start with is integration by parts. So this is going to be split into two videos. The first video, we're just looking at the main ideas, and then in the second video, we'll have some more advanced but less common applications. So let's get started. Like a lot of rules for integration, it comes from reversing a rule for differentiation. So in particular, integration by parts comes from reversing the product rule. So let's just remember what the product rule says. It says that if we want to differentiate, a product of two functions, it's not the product of derivatives, but instead we have to differentiate them one at a time. Or in other words, we fix one function, say f, and differentiate the other g, and then vice versa, we fix g and then we differentiate f. So we have these two terms. So all we then do is we rearrange. So if we keep this one term fixed, this f of x times g prime of x, and then move the g of x times f prime over to the other side, we end up with f times g prime is equal to this derivative of the product minus g times f prime. So all we did was move this equation around. So we have fg prime is the derivative of fg minus g times f prime. And then we're going to integrate both sides. So, and by integrate, remember we had two integrals, the definite and the indefinite integral. So here we're going to do the indefinite integral. So we just take the indefinite integral of everything. So if we take the indefinite integral of the left side, we get the integral of f times g prime. But then on the right side here, if we do the indefinite integral of the derivative of the product, remember the indefinite integral just meant an antiderivative. So we're looking for, when we do the indefinite integral of this, we're looking for an antiderivative of the derivative of the product. Or in other words, it should just be f times g itself, right? An antiderivative of a derivative is just fg. And then, okay, as before, if we take the indefinite integral of g times f prime, here is the indefinite integral of g times f prime. And you might say, okay, what about the plus c here when I integrate this derivative? But because we have an indefinite integral on the left, there's a plus c, indefinite integral on the right, there's a plus c. There are already c's floating around, so we don't need to add more plus c's. So this is okay. And this is all the integration by parts formula is. So this formula is called the integration by parts formula, and sometimes to save time, we'll call it IBP. So IBP for integration by parts. And why is this useful, for instance? Well, it doesn't always tell you how to do the integral, right? It tells you how to do this integral in terms of some other integral. But the advantage is that the second integral on the right, if we make some good choices, if it's a good example for integration by parts, the integral on the right could be simpler, right? So the one we started with is f times g prime. Okay, and then here's something we can calculate, but then the integral that we have on the right is g times f prime. So this is a different integral, and in some examples it will be simpler. So that's why it's useful. Firstly, I want to mention that there's another way of writing integration by parts that some of you might have seen if you've seen this before, or you might see in other places. I'm not going to use it, I just want to make you aware of it. So suppose we write u equals f of x and v equals g of x. Then we would have du of dx equals f prime, which you could kind of formally rearrange to be du equals f prime of x dx. And okay, if v equals g of x, you could differentiate, you get dv of dx equals g prime of x, or you could kind of formally rearrange and write that as dv equals g prime of x dx. And then we could just rewrite these formulas with u and du and v and dv. So f becomes u, g prime times dx becomes dv, so we get u dv. F times g becomes uv, g becomes v, f prime of x times dx becomes du. So it's equivalent to write the formula as integral of u dv equals uv minus integral of v du. But I'm probably not going to think about it that way. Yeah, so as we said, this is useful if the integral on the right is simpler than the one we started with. And okay, if we see an example where we have to use integration by parts, we're not going to be told what is f and what is g prime, right? We're just going to see something we have to integrate. We have to try to recognize it as a product of two things. And then we have to pick one of the terms in the product to be f and one of the terms in the product to be g prime. So that's a choice that we have to make. So how should we make it? Well, we want the integral on the right to be simpler. So to get this integral on the right, we're looking at f prime instead of f. So try to pick f as something that gets simpler when you differentiate. That's my rule of thumb. And if it doesn't work, then you can always go back and make the opposite choice. But when you're starting, just try to pick f as a thing that gets simpler as we differentiate. And you can remember this as the formula. Please do remember the precise formula. But another way to think about it is, right, we're starting with the product. We have to recognize two terms. And then what do we have to do to get whatever is on the right? We're going to pick a function to differentiate and a function to integrate. And then the first term, we just do the integration of one term. But then on the integral that we have left, we have to both differentiate one term and integrate one term, right? Here we differentiate the f and we integrate it to g prime. So on the right side, we're going to integrate one of the terms. And then on the second integral, we're going to have to differentiate one term and integrate one term. Okay, so let's see how it plays out in some examples. So for instance, here, let's try to find the integral of x times sine x. So it's not anything we can do with calculus 1 techniques. We have to use integration by parts. And luckily, we can see straight away that it's a product, right? It's x times sine x, so it's a natural product. So we want to pick one of the terms as something we're going to differentiate and one as something we're going to integrate. And clearly, the x gets simpler as we differentiate. It becomes 1, so that should be the term we differentiate. So let's choose f of x to be x. And let's choose the derivative that we're about to integrate. G prime of x is going to be sine x. So we're going to differentiate the x, integrate the sine x. Okay, we fill in the boxes. F prime is going to be 1. G of x is going to be minus cosine x. Right, if we integrate sine x, that's minus cosine x. Okay, and then we want to use the integration by parts formula. So if you remember what the formula was, integral of f times g prime equals fg minus the integral of g times f prime. Or if we just want to kind of think about it in our heads, right, what do we have to do? So here I copied in the terms, use it from the formula. But what do we have to do? Okay, we're fixing one term we're going to differentiate, one term we're going to integrate. On the first term, without any integrals, we have to do one integration, but not do any differentiation. So we're integrating the sine, so we get minus cosine x. So we have x times minus cosine x. And then we have to subtract the integral where we differentiate one term and integrate one term. So here we are differentiating the x, integrating the sine x, so we have 1 times minus cosine x. So here on this first line, we just applied integration by parts. So do be careful with the minus signs, right? Integration by parts always carries a minus sign. And then if you get a minus sign inside the integral for some reason, then you're going to want to make sure you track the minus signs carefully. So it never hurts to add more parentheses. Okay, then we clean this up. We have a minus and a minus, so that becomes plus the integral of cosine x. And then we do the integral of cosine x, which is way easier than the integral we started with. Okay, integral of cosine x is just sine x plus c. So in the end, we get the answer as minus x cosine x plus sine x plus c. And as usual with indefinite integral problems, we can always check this answer by differentiating, right? The indefinite integral just represents an antiderivative. So if we differentiate what we ended up with, we should get back to where we started. So you could check, for instance, using the product rule, that this really differentiating becomes x sine x. Okay, but here this was dependent on the choice f of x equals x, g prime of x equals sine x. We were going to differentiate the x and integrate the sine x. Let's just see what would have happened if we'd done it the other way around, why it wouldn't have been helpful. So we have the same example. Let's suppose we make the opposite choice. So instead of differentiating x, let's integrate the x and let's differentiate the sine x. So we're going to choose f to be sine x, g prime to be x, f prime to be cosine x. Then g of x is going to be a half x squared, right? If we integrate the x, we get a half x squared. So we apply integration by parts. The first term, we just do one integration. So we are integrating the x. So we get a half x squared times sine x. And then we have to take away the integral where we integrate one term and differentiate the other term. So if we integrate the x, we get a half x squared. If we differentiate the sine x, we get cosine x. Okay, this is still a true formula, but now the integral that we ended up with is even harder than the one we started with. So it's still true, but it doesn't help us. So we want to, if you see this happening, you get something that's even harder than what you started with, you want to try to maybe go back and make the opposite choice. So the choices of which time to differentiate, which time to integrate, really, they do matter. Okay, so let's go on to next kind of, so there are some tricky examples where there are some extra techniques we have to keep in mind. So for instance, integrating ln x is a classic example with integration by parts, but it's not a product. We don't see straight away the product, so we need some kind of sneaky trick to make this into a product. And the sneaky trick is to write it as ln x times 1. So anything is equal to itself times 1, so we can kind of make anything look like a product, even if it's just kind of artificial, just by writing it as times 1. Okay, now we see we have a product. So we have to decide what we should differentiate and what we should integrate. And it looks tempting to differentiate the 1 because 1 gets way simpler. It becomes 0 when we differentiate. But the problem then would be we would have to integrate the ln x. And that's the problem we have. We don't know how to integrate ln x. So that will be a bad choice. So the natural choice here is to differentiate the ln x and integrate the 1. So let's see how that plays out. So we're going to differentiate ln x. We're going to integrate the 1. We fill in the table. When we differentiate ln x, we get 1 over x. If we integrate the 1, we get x. Okay, let's plug that in our formula. So remember the first term, we're just going to integrate. So we are integrating the 1, we get x times ln x. And then we subtract the integral where we differentiate and integrate. So we are differentiating ln x, we get 1 over x. We are integrating 1, we get x. So we have x times 1 over x, which of course becomes 1. So we have to do the integral of 1. Okay, an integral of 1 is easy, way easier than the integral of ln x. It's just x plus c. right? So in the end, we get x ln x minus x plus c. Careful with the minus signs and make sure we always keep the first term as we work. Okay, so yeah, so here is a hidden product. If you have something that doesn't look like a product, but it is something that gets simpler as you differentiate, you can always try to write it as that thing times 1 and do integration by parts that way. Doesn't always work, but it works in a few examples. Okay, another technique is sometimes we might have to use integration by parts twice. So for instance, let's try to find the integral of t squared cosine t. Then in this case, t squared gets simpler as we differentiate, it becomes 2t. And then if we differentiate again even, it will become 2. Cosine t doesn't really make much difference if you differentiate or integrate. It's still kind of the same degree of complexity, or it's going to be sine or minus sine and so on. So let's try to differentiate the t squared and integrate cosine t. And I'm not going to write everything out, but let's see what we get. So remember on the first term, we don't do any differentiation, but we want to integrate one term. So we are integrating the cosine t. So we get sine t. So we get t squared times sine t. And then we take away the integral where we both differentiate one term and integrate the other term. So we are differentiating the t squared, we get 2t. And we are integrating the cosine t, we get sine t. Okay, this is simpler than what we had, but it's still pretty complicated. So we have to do integration by parts again, completely independently of whatever is going on here. So let's forget what we just did and figure out 2t sine t indefinite integral using integration by parts. So if we do that, we're going to differentiate the 2t and integrate the sine t. Make sure we're doing the same type of term. Right here, we're differentiating the polynomial. Here again, we're going to want to differentiate the polynomial. If you switch it around, you'll end up back where you started. So differentiate 2t, integrate the sine t. Remember, on the first term, we only integrate one term, so we get minus cosine t. So we have 2t times minus cosine t, that's going to be minus 2t cosine t. And then we take away the integral where we both differentiate and integrate. So we're differentiating 2t, we get 2. We're integrating sine t, we get minus cosine t. So here's our new integral. Okay, there are some minus signs we should track. So the minus and the minus cancel. We end up with the integral of 2 cosine t. So that's going to become 2 sine t plus c. So we managed to find this integral now. But this wasn't the problem, right? The problem was to go back and find this original one. So we have to put them together. So the one we're after is t squared sine t minus this integral. And this integral is the thing we just worked out. So we basically want to go back and plug this in here. So because we don't have plus the thing we just worked out, we have minus the thing we want to work out. We just worked out. So we're going to have to track the minus signs, right? So we're going to have minus 2t cosine t. So we're going to get a plus. And then we have minus 2 sine t. So we're going to end up with a minus. Okay, so that's all we did here. We just combined the two formulas, and where there was the integral of 2t sine t, we plug in whatever we find that to be down here. And it doesn't really matter if you have plus c or minus c or plus 2c or anything like that, because c is just an arbitrary constant. So I'm not going to replace that by minus c. It wouldn't be wrong if you did, but doesn't. If you have 5c, 10c, a million c, minus c, it doesn't matter as long as it's arbitrary constant. Okay, so onto the last thing for this video is we have indefinite integrals and we have definite integrals. So, and they're very closely related. So how do we find a formula for definite integrals? So remember that if we want to find a definite integral, which is just the integral from a to b, fundamental theorem of calculus says all we have to do is find the antiderivative and then plug in the endpoints and subtract them, right? That's what we do to find any definite integral. We do the antiderivative, plug in a, plug in b, and subtract. But another word for antiderivative is just the indefinite integral. So all we have to do is take the formula we already had and plug in a and plug in b and subtract, and that's going to give us a new formula for the definite integral. So I'm not going to go through all the steps, but here is the formula, and it's pretty similar. It's pretty much the same as the formula we already had, right? Instead of indefinite integrals, there are definite integrals from a to b. And instead of just f times g, there are these square brackets around with a and b. So this just means plug in a, plug in b, and subtract them, right? So it's going to be plug in b, plug in a, sorry, this should be f of x times g of x. Plug in b, plug in a, and subtract, we get f of b, g of b minus f of a times g of a. Okay, so that's everything becomes a definite integral, and then we have to remember to plug in the endpoints on this first term. So let's do an example of that. For instance, we integrate inverse tangent of x from 0 to 1. Okay, it doesn't look like a product, but inverse tangent does become simpler as we differentiate, so we should try to write it as, hidden product, write it as 1 times arctan x. And then we're going to want to differentiate the arctan and integrate the 1 because we don't know how to integrate arctan right now. So we differentiate the arctan, integrate the 1. We fill in the boxes. Okay, we differentiate arctan, we're going to get 1 over 1 plus x squared. We integrate the 1, we're going to get x. Let's plug that into our formula and just focus on the top line first. So remember on the first term, it's the same as always. the same as before, right? We had 1 times inverse tangent x. We have to integrate one term. We don't do any differentiation on that first term. So we integrate the 1, we get x. So we have x inverse tangent x, except now we have to evaluate in a minute between 0 and 1. And then we have to subtract the integral where we both do a differentiation and an integration. So we're integrating the 1, we got x, and we're differentiating the arctan, we get 1 over 1 plus x squared. So we end up with x over 1 plus x squared. Okay, and then from there, it's just calculating what these two pieces are. So for instance, on the first term, we're plugging in 1, we get 1 inverse tangent of 1. So here is the inverse tangent of 1, minus 0 inverse tangent of 0. So anything multiplied by 0 is going to be 0, so that disappears. So all we did is plug in the 1, plug in the 0, subtract. And then this integral is something that we can use integration by substitution on. So for instance, you could do u equals 1 plus x squared, and it will come out as a very nice substitution integral. So I'm not going to go through that right now because it would be a distraction. But you could check with substitution, and the answer is a half ln2. So this integral becomes a half ln2. Okay, and then we have to figure out what is arctan of 1. So to find arctan of 1, we have to figure out what number we plug into tangent in order to get 1. Okay, that will be pi over 4. So in the end, we get pi over 4 minus a half ln2. But the key point was, or the new point was just integration by parts with definite integrals works the same way as with indefinite integrals, except we keep the limits on the integrals, and when we don't have the integrals, we have to make sure in the term that doesn't have the integrals, we have to plug in the endpoints and subtract them. And do be careful with the minus signs, as usual. Okay, so that's everything I wanted to talk about for the key points on integration by parts. In the next video, I'll talk about some kind of more involved examples, but these are the key ideas. Thanks, everyone. See you next time.